Imagine you're pushing water through a tiny glass straw, swiping your finger along the inside first. When you start your flow, you might notice the water sticks differently the second time, almost as if the straw remembers your first pass. In microflows, this isn't just fingerprint trickery, it's the boundary layer memory effect, where the thin layer of fluid hugging a surface retains a hint of past flows and subtly steers what happens next. What gives a boundary layer memory? At the micron scale, molecules near the wall don't bounce off and forget instantly. They adsorb, align, or even deplete depending on the shear and chemical environment. Question, could those rearranged molecules really stick around? Answer, absolutely. Polymer chains can lay flat on a surface after a high shear event, and surfactant molecules can lock into new patterns, both altering the next flow's slip or how freely fluid glides along the wall. How does this influence future behavior? Imagine you first pump a fluid with long polymer strands. Under shear, the polymers stretch and coat the wall, reducing friction. Your effective slip length grows. If you reverse or restart the flow immediately, that polymer layer is still there, making the next run smoother than the first. That's hysteresis in action. The flow rate versus pressure curve won't trace the same path forward and back. Where do we see this in practice? Dynamic wetting. A droplet creeping along a microchannel can leave behind a trail of surfactant, changing the contact angle for the next droplet. Time-dependent slip. In nano-lubrication, water confined between hydrophobic walls can slip freely at first, but after minutes, dissolved gases or ions accumulate, reducing slip dramatically. Electro-osmotic flows. Repeated electric field pulses rearrange the ion cloud at the surface, shifting the zeta potential, and so the flow speed at a given voltage each time you pulse again. Why aren't our models capturing this? Classic Navier-Stokes with a fixed no-slip or constant slip boundary condition assumes the wall is a blank slate each instant, but in micro and nanoflows, the wall and near-wall fluid evolve on comparable timescales to your experiment, so you need dynamic boundary conditions, rules that say slip length equals F past shear, time since last flow. To predict real behavior, can we harness boundary layer memory? Absolutely. By preconditioning microchannels with a tailored primer flow, say a surfactant solution under high shear, you can engineer an ideal slip profile for rapid mixing or selective particle separation. In lab-on-a-chip devices, this lets you switch between high-speed transport and gentle handling simply by tuning your flow history rather than remaking the channel surface every time. In the end, boundary layers in microflows are not amnesiacs, but chroniclers of past stresses. To master microfluidics, we must write that history into our equations. Embracing time-dependent slip, dynamic wetting, and the beautiful complexity of flowing memory. In fluid dynamics, the boundary layer is the thin region near a solid surface where fluid velocity transitions from zero, no slip condition, to free stream velocity. In microfluidic systems, this region often dominates the overall flow behavior due to the high surface-to-volume ratio. It's where shear forces, surface tension, and interfacial dynamics are strongest. Unlike bulk flow, the boundary layer is sensitive to surface chemistry, topology, and molecular. It serves as the interface between fluid mechanics and material science. In microchannels, over 50% of viscous dissipation can occur within the boundary layer despite its nanometer scale thickness. It's like the layer of people near the walls at a crowded party. What happens there sets the tone for the whole room. Traditionally, boundary layers are treated as instantaneous responses to current flow conditions. However, evidence suggests that they can retain information about previous flow events, especially under time-varying or oscillatory regimes. This memory may manifest as hysteresis in slip velocity, dynamic contact angles, or surface charge relaxation. These effects are not captured by classical Navier-Stokes models with steady-state boundary conditions. They hint at a more complex history-dependent behavior driven by molecular or viscoelastic processes. Experiments with water-glycerol mixtures show different slip lengths depending on whether flow is increasing or decreasing in microchannels. It's like a rubber band that stretches differently the second time it remembers the stress. In many microfluidic systems, slip at the wall is not constant but varies with time, flow history, or shear rate. Time-dependent slip can occur due to rearrangement of interfacial molecules, depletion layers, or dynamic polymer brush conformations. When flow is reversed or modulated, the slip boundary condition does not always return to its original state immediately, leading to hysteresis. This memory-like behavior is especially pronounced in complex fluids, surfactant-laden interfaces, or near-soft deformable walls. It complicates predictive modeling. Slip length in hydrophobic microchannels can double or halve, depending on the duration and intensity of the prior shear. It's like a fingerprint on glass. Once touched, the surface reacts differently, even if wiped. When liquids advance or recede over surfaces, the angle at which the interface meets the wall, contact angle, can depend on the flow history. This is known as dynamic contact angle hysteresis and can persist over seconds or minutes. It reflects molecular pinning, interfacial rearrangement, or trapped microbubbles that don't immediately relax. Since the contact line resides in the boundary layer, it contributes to boundary layer memory. Time-lagged wetting responses are common in biofluids, inks, and reactive solutions. A droplet moving over a chemically patterned surface shows asymmetric wetting angles depending on direction of motion. It's like a footstep in sand. The imprint doesn't vanish instantly after the foot is lifted. In polymer solutions or surfactant-rich systems, the boundary layer can store elastic or chemical stress due to internal molecular relaxation times. These effects cause memory of past shear events to persist through slow reconfiguration of chains or micelles. The resulting flow response can include delayed stress recovery, recoil motion, or oscillatory dampening. These memory effects are intrinsic to the material properties but expressed at the boundary interface. They create coupling between time, stress, and flow. Worm-like micelle solutions in microflows exhibit recoil and secondary flow structures even after flow is stopped. It's like memory foam. You press it once and it remembers your shape for a while. Electrokinetic flows involve charged boundary layers, the electric double layer, which can store ionic configurations that evolve over time. Past flow events can polarize the double layer, generating long-lived streaming potentials or ion imbalances. When flow resumes or reverses, the electric field and fluid motion interact in a time-dependent way. This electrokinetic memory can affect electrophoresis, ionic pumping, and microfluidic sensing. Classical electrohydrodynamics often underestimates these effects. In nanochannels, a single pulse of flow can alter surface charge distribution, affecting later electroosmotic mobility. It's like a capacitor charged by flow, drained slowly, but never quite back to zero. Most fluid simulation frameworks treat the boundary layer as a passive, instantaneous element governed by fixed parameters like slip length or no slip condition. If memory effects are significant, this assumption breaks down, requiring history-dependent or integra-differential models. These models would need to track time-dependent variables like interfacial stress, conformation states, or adsorbed layer. Such complexity introduces computational challenges, but may be essential for accurate predictions in micro and nanofluidics. Incorporating these effects would shift simulations closer to real-world fidelity. Lattice-Boltzmann models extended with viscoelastic memory terms more accurately reproduce observed wetting hysteresis in nanochannels. It's like adding memory to a computer program. You cannot just input the present, you must remember the past states too. Understanding boundary layer memory could improve performance in lab-on-chip devices, microreactors, biosensors, and soft robotics. Memory effects might be exploited for time-enclosed sensing, flow history tagging, or fluidic logic systems. Experimental methods like high-speed micro-PIV, surface force microscopy, or fluorescent tagging can now resolve subtle hysteresis and flow delays. Tailoring surfaces to tune memory, e.g. with switchable coatings or smart polymers, opens doors to programmable flow behaviors. New technologies may use boundary layer memory as a feature, not a flaw. Programmable microfluidic valves using surfactant hysteresis retain open or closed states depending on flow history. It's like a thermostat that remembers when the room was last hot and adjusts more gently next time. Far from being static buffers, boundary layers in microflows appear to possess dynamic memory of previous conditions. Whether through molecular lag, ionic polarization, or mechanical hysteresis, they create time-dependent behaviors not predicted by traditional models. This reveals a new layer of complexity and opportunity in designing microfluidic systems and understanding natural flow phenomena. Accounting for memory may lead to smarter, more responsive materials and devices. In fluid dynamics, the past may quietly shape the future. In biomimetic systems, boundary layer memory can help mimic vascular autoregulation or dynamic mucus transport. It's like writing on water, but the water remembers the strokes even after the ripple fades.